Hey, hey, what's up, SUPA people? Welcome to the next edition of SUPA Chemistry. So here we go. We're going to kind of pick up with what we were doing last time. We were dealing with some stoichiometry stuff. So we're going to continue with that. We're going to learn percent yield and then limiting factors. Right? And it's really building off the stoichiometry stuff that we dealt with last time. So percent yield is very similar to percent error. Oops. Okay, it's similar to percent error, and it's a formula. So my percent yield is equal to the experimental yield divided by the predicted yield times 100. Well, sometimes these have different names. So instead of experimental yield, okay, this is our measured yield. Okay, so this is the one that we usually, this is the one we do in lab, okay, or the experimental value. Okay, sometimes that's what it's called. The bottom one is sometimes called the theoretical yield. What should have happened? How much should we have gotten in the reaction? So this is what we did get when we did the reaction. This is what theoretically we should have gotten. Okay, and I'm going to show you how to calculate this. And we're going to use stoichiometry to do it. We'll use a problem. So let's say we have 8.0 grams of methane combusts, and we collect 17.0 grams of H2O. What is the percent yield? So the very first thing we really need is we need the equation. Right, so we have methane is CH4. It combusts, so we're adding oxygen. We know that that's going to produce carbon dioxide and water. When we balance this, we need a 2 here and we need a 2 here. Right. So now, we're starting with 8 grams of methane. And we're producing carbon dioxide and water, but it tells us that we produce 17 grams of water. Well, I want to know if all of this CH4 actually reacts, how much water should I have gotten? All right, that's what's called the theoretical yield. So we're going to use this stoichiometric ratio to figure out how much water I should have gotten. So I'm going to say, hey, look at how much should I have gotten? I'm going to make that X. Now this is a chart problem. Okay. Now I'm going to be smart. Remember, this is moles, this is total mass, and this is volume of gases. Now I'm going to be smart. I don't need any of this. Okay, I'm not going to use oxygen right now, and I'm not going to use this. All right, so my X, okay, is in grams. Okay, so that's what I'm worried about. This is in grams, so I don't need moles. I don't need volume. So these are the only 2 boxes I have to fill in. The total mass of CH4, all right? And there's only 2 sig figs, so I'm just going to round. So this is 16 grams. And the total mass of 2H2O, which is 36 grams. Okay, so I want to calculate my theoretical yield. So I'm going to take 8.0 grams over 16 grams equals X over 36 grams. Right? So this is of my methane, this is of my water, and when I cross multiply, it turns out I should have gotten 18 grams of water. Now when I actually did the experiment, I only got 17 grams of water. So something went wrong. I didn't produce enough water. By the equation, I don't know what it is, all right, but we can see, we can do what's called percent yield, and it'll give us an idea of how good or bad we did. So now it's easy to stick in percent yield is equal to our experimental yield, and you can just put experimental over predicted or theoretical, I don't care, times 100. So our experimental yield is what we got. This is our experimental yield. It's what we got when we actually did the reaction. That goes on top. Predicted yield is our theoretical yield. That goes on the bottom. When we do that math, we get 94.4%. Now, what do we want our percent yield to be? Well, we want our percent yield, we want it to be 100%. Okay, we want this to be 100%. If our percent yield is over 100%, that means our experiment made too much. If it's below 100%, that means the reaction didn't go to completion and we didn't make enough. Okay, so this is percent yield. Let's try another one. When 9.30 grams of magnesium metal reacts with hydrochloric acid in excess, it produces 0.771 grams of hydrogen. What is the percent yield? Okay. So the very first thing you have to write the equation. So we have magnesium metal reacting with hydrochloric acid, which is HCl aqueous. Right? This is single replacement, so the Mg is going to go with the Cl, and we crisscross that, and we get MgCl2 plus H2 gas. Right? So here's my equation. We need to balance it, so I'm going to need a 2 here to balance that. Now, let's go back into an equation. So I'm starting with 9.30 grams of magnesium. It's just red. And it tells me that the hydrochloric is in excess. Now, what does that mean, in excess? Well, what that means is there's enough HCl available to react with all of the 9.30 grams. All right, so what that's just saying is that, okay, we're going to keep adding acid, okay, keep adding acid until we've used all of the magnesium. All right, so this is what we did in lab. All right, so in the lab that we did in class, right, we had HCl and we kept adding the HCl until all the magnesium was gone. So that means this was in excess. We had enough of it to react with all of that. Now, we want to know the theoretical yield, or the predicted yield. Oops. Okay, So what is this right here in the problem then? This is my experimental yield. It's what we actually get when we did the experiment. So for our experimental yield, okay, we have to do a chart problem. We want to know how much hydrogen in grams we should get. Now, I'm going to do a shortcut. Instead of making out the whole chart and crossing things off, now can't I just say, hey, look, I know I need to have the total mass of magnesium. Okay, the total mass of magnesium is 24.31. And for hydrogen, it's 2.02. So now I can just set up my ratio of 9.30 grams over 24.31 grams equals X in grams over 2.02 grams. When I do that math, 9.30 times 2.02 divided by 24.31 equals 0.773 grams. So this right here is what I should have gotten. That's what I should have gotten. What did I get? Well, I only got 0.771 grams. So I can figure out, hey, how close was I? Well, my percent yield equals my experimental over my predicted times 100. Here's my experimental, 0.771 grams, divided by what I should have gotten, 0.773 grams times 100. And it turns out that it's 99.7%. So I did pretty good, because remember, 100% is what we're aiming for. So we did pretty good in this reaction. This is called percent yield, and it's really just a way to check your work. Right? It's to check your data on how well you did in your reaction. Okay. The next thing we're going to talk about is just kind of another, it's doing the same sort of kind of thing. It's, again, using stoichiometry. And this is called limiting factor. Limiting factor. Now, in limiting factor, you will be given an equation with specific amounts of each reactant. The reactant that is used up first is the limiting reactant or limiting reagent or the limiting factor. It's all the same thing. Limiting reactant, limiting reagent, limiting factor, they're all the same thing. Now the one that has stuff left over is in excess. Okay? It's the one in excess. We have extra of it. So now, before we do a problem, I just want to show it to you this way. So let's look at these guys. Okay, so let's see that these are my reactants. Okay, so I got a nut and a bolt. All right, and these are going to react to form a compound. Right, so this is going to keep reacting. These are going to keep reacting until we run out of one of them. All right, so this one will go with this one. 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 And then finally this one will go with this one. Now, after that, the reaction stops. Why does it stop? Well, we've run out of bolts. We still have some extra some nuts over here. All right, we still have some of these, but we've run out of this. So as soon as we've run out of the bolts, okay, this reaction stops. I can't make any more of this. The bolts would have been my limiting factor. The nuts, okay, these would have been in excess. Right, so the reaction stops, okay, as soon as we run out of our limiting reagent. Okay, that's what dictates how many products we made. All right, so the limiting factor dictates how much stuff we can make. Right, and this is going to be left over. Okay, so that's just kind of a visual for you. Let's put it into practice. So let's try this problem. You have 6.0 moles of sodium and it reacts with 10.7 grams of chlorine. How much NaCl in grams is produced? Well, just like we've been doing, we need the chemical equation. All right, so this is actually a combination or a synthesis reaction. So we're going to take Na and we're going to react it with chlorine. Remember, chlorine is a diatomic. Okay, and it's going to produce NaCl. We need to balance, so this has to be a 2 and this has to be a 2. So there's my balanced equation. Right. Now, this is a stoichiometry problem, and there's a couple ways that we can attack it. So let's go ahead and draw volume, total mass, and moles. So just for fun, let's put up here, we have 6.0 moles and we have 10.7 grams of chlorine. So let's go ahead and fill out our chart. So I need moles in this one, so this would be at 2 moles. I need grams in this one, so let's see, chlorine is what? 35.45 times 2 gives us 70.9. Oops, 70.9 grams. Eventually, we really want to know, hey, how much NaCl can be produced? So there's a couple ways that we can figure this out. All right, so the first thing, you could do it this way. You could say, hey, look, let's set up 2 ratios because I want to know how much this in grams is produced. One of these is a limiting factor. So let's set up 2 ratios. Let's use this one first to see how much is produced. And then let's use this one and see how much is produced. All right. Now, I'm going to need this number right here. So Na is 22.99 plus Cl, what we say is 35.45 times 2 is 116.88 oops, wrong spot, 116.88 grams. All right, so let's figure out how, theoretically, okay, let's figure out theoretically how much NaCl should be produced with if I have 6 moles of Na. So I'm going to do this one first. Well, 6.0 moles over 2.0 moles equals X in grams over 116.88 grams. So if all the sodium was used, 116.88 times 6 equals divided by 2 equals 350.6 grams. And that's off with sig figs, but that's okay. So if all of this 6 moles of Na reacted, I would get 350 grams of NaCl. Well, what if the chlorine reacted? Okay, let's do the same thing except with the chlorine. We'll set up our ratio. 10.7 grams over 70.9 grams equals X in grams over 116.88 grams. Well, 10.7 times 116.88 equals divided by 70.9. We get X equals 17.64 grams. And this would be of NaCl. So now let's look at this. What is this telling me? Well, if I used all of the Na, it would be able to produce 350.6 grams. If I used all of the Cl2, it would only make 17.64 grams of NaCl. The one that makes the less is the limiting factor. All right, so this guy makes less. So it will run out first. Which means the Cl2 is the limiting factor. This is the most I could make. In other words, I'm going to have extra Na left because there won't be any more Cl2 to react it. So we will run out of we will run out of Cl2 and the reaction will stop. Okay, so the Cl2 is the limiting factor, or the limiting reagent, and the Na is in excess. Now I want to show you another little trick, and I kind of don't have room, so I'm going to just do it right down here. Okay, if you're trying to figure out the limiting factor, there's another way that you could do it. All right, so I know that I have this much Na, and I know I have this much chlorine. Right? So I could just say this, look it, I'm going to set up a ratio, and I'm going to pick one. It doesn't matter which one. So I'm going to pick the Na. I'm going to say, okay, if I have 6.0 moles of Na over 2.0 moles of Na, how many grams of Cl2 do I need to completely react with it? And this is 70.9 grams. And if I just quick do that math, it turns out that I would need 210 grams of Cl2 to react with 6 moles of Na. Do I have 210 grams of Cl2? No, I only have 10.7 grams. So I only have 10.7 grams, which means this is my limiting factor again. It's just another way to figure out which of your two reactants is your limiting factor. So let's try another one. say we have 7.30 moles of sodium hydroxide. And 274.7 grams of sulfuric acid. Which react? What is the limiting factor? And how many moles of water will be produced? Well, again, we have to start with our equation. All right, so our reactants are sodium hydroxide and sulfuric acid. So we're reacting an acid and a base, which is neutralization, okay, and it's going to produce salt and water. It's double replacement. So sodium hydroxide. Okay, sodium is Na and it's +1. Hydroxide is OH -1. You crisscross that and we get NaOH. Plus sulfuric acid. Well, this is a polyatomic, so it's 8 goes to ic, so this is sulfate. So this is H, which is +1, SO4, which is -2, and we get H2SO4, and that would be aqueous. So this is double replacement, so the Na is going to go with the SO4, and we crisscross that, +1 -2, so we end up with Na2SO4 and HOH. We balance this, we need a 2 here, and we need a 2 here. All right, so there's my balanced equation. Now, I know that I have 7.30 moles of NaOH. And I know that I have 274.7 grams of H2SO4. Right now, I need to know which is the limiting factor, and then I want to know how many moles of this is going to be produced. Now, why do I have to know the limiting factor? Well, the limiting factors determines how much water it's produced, so I have to figure out my limiting factor. And I'm going to do my quick shortcut. Now again, you need to make the chart, but I'm to the point where I know I need moles. Right? So for this ratio, it's going to be moles, which is 2. This one is in grams, so I need total mass of this. I need total mass of this. So oxygen is 16. Plus sulfur, which is 32.06. Plus hydrogen, which will be 2.02, and that gives me 98.08. Grams, this was moles. And I might as well do this one, all right, because I'm gonna need it. Okay, so this would be 2 moles. So now, we need to figure out our limiting factor. And this is what I would do. Okay. I'm going to say, hey, look at how much H2SO4 do I need to react with 7.30 moles? So I'm going to say, look at, I have 7.30 moles of NaOH over 2 moles. And I want to know in grams how much H2SO4 I would get. So if I did 7.30 times 98.08 divided by 2, I would get 357.99 grams. I would need that much H2SO4 to react with all the NaOH. Well, how much H2SO4 do I have? Well, I only have 274.7 grams. So I'm going to run out of this one. And as soon as I run out of the H2SO4, the reaction stops. So this guy is my limiting factor. That's the one I use to calculate the amount of product. So I'm going to use this ratio, 274.7 grams over 98.08 grams, X in moles over 2 moles. 274.7 times 2 divided by 98.08. We get 5.602 moles. That's how much water would be produced. Okay. That's how much water should be produced. Okay, so this would be my limiting factor. Now, when you're figuring out your limiting factor, you could have done what we did the first time. I could have set up a ratio with this in water. Then I could set up another ratio with this one in water and see which one made less. The one that made less is your limiting factor. It doesn't matter which way you do it. It's fine, whichever way you prefer. All right, let's try one more. Let's do one more problem. You have